In deciding whether sequence, or in this case series, converge or diverge, we talk a lot about how you need to add less and less and less, and eventually you add so little that it's considered zero. Well, that's kind of the concept behind the ratio test. We let the summation n equals 1 to infinity of a sub n be a series of non-zero terms. There are three cases that we have. Number one, if the series converges if the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1. The series diverges if the same thing is greater than 1. On number 3, the ratio test is inconclusive if it is exactly 1. Now what this means is, consider some series. Let's say it's a geometric series. We have 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32, and we keep adding less and less and less and less, and eventually we add so little that it's considered zero. But take any two of the numbers and test the ratio. If we have 1/4 divided by 1/2, 1/4 divided by 1/2, multiply the top and bottom by 4, those cancel. That becomes a 2. So the ratio for each of them, what we're multiplying by, is 1/2, and that's how we already knew that since it was a geometric series. But if you take any of these two, if the ratio is less than 1, then this thing is adding less and less and less each time. If it's greater than 1, then we might have something like, well, if you take 2 plus 4 plus 6 plus 8, take 6 divided by 4, that's 3/2. That's bigger than 1. So that means that we're shooting off to infinity, and this thing is going to diverge. This test is used when we see factorials usually. So let's dive right in. Let's take the limit as n approaches infinity, and the ratio test says add 1 for n. In other words, let's find the next term. The next term would be 2 to the n plus 1 over n plus 1 factorial, and divide that by the previous term, 2 to the n over n factorial. And if this ratio is greater than 1, then this thing is shooting off to infinity and it's diverging. Well, instead of dividing, we really want to multiply by the reciprocal. So this becomes 2 to the n plus 1 over n plus 1 factorial, and then we'll do, instead of divide, we'll do times, and it'll be n factorial over 2 to the n. Now let's take the 2's first. When you divide the same base, you subtract the powers. So we really have n plus 1 minus n. So that's going to leave 2 on the top. So we have limit as n approaches infinity of 2 on top, and then on the bottom we can make this n factorial and then times the next one. That really would be n plus 1 factorial. Now the n factorials are going to cancel out, and we have the limit as n approaches infinity of 2 over n plus 1. Now that is equal to 0 because the denominator is going to be getting bigger and bigger and bigger, and that makes this fraction smaller. And 0 is less than 1, so the series converges by the ratio test. In our next example, we're just going to do a couple of these. Limit as n approaches infinity of, now I'm going to multiply by the reciprocal right away instead of writing division, but first we have to do the n plus 1 term. So we have n plus 1 squared, 3 to the n plus 2 over 2 to the n plus 1. Now instead of dividing, like I said, we'll multiply by the reciprocal right away. So we have times 2 to the n over n squared, 3 to the n plus 1. Alright, what should we do first? How about the 3 first? If you have 3 to the n plus 2 divided by 3 to the n plus 1, we're going to subtract the powers again. So we have 3 plus 2 minus n plus 1, which is n minus n. 2 minus 1 is 1. So we have 3 on top. And by subtracting the powers with the 2's, we will have 1, 2 on the bottom. And we are left with n plus 1 squared over n squared. Now when we take the limit of a rational function, that's pretty much what we have left over. We're going to use our ending behavior laws. If I expanded this out, it'd be n squared plus 2n plus 1. But the leading power would be n squared, so the ratio would be 3/2. So the limit, I don't even need to write that now, the limit of this is 3/2, which is bigger than 1. So now we know that this series diverges by, not nth term test, the ratio test. One more example. We have the limit as n approaches infinity of the absolute value of n plus 2 factorial over 3 to the n plus 1, and then instead of dividing, which we should do, we'll just multiply by the reciprocal of this, which is 3 to the n over n plus 1 factorial. How about we deal with the 3's first? Limit as n approaches infinity, the absolute value of, when we subtract these two, now there's 1 extra in the denominator instead of the numerator, so that puts 3 in the denominator. On top we'll have n plus 1 factorial, but then times n plus 2. And that'll be over n plus 1 factorial. That's equal to the limit as n approaches infinity of, let's see, the n plus 1's will cancel out, and we're left with the absolute value of n plus 2 over 3. And this is now shooting off to infinity, which is clearly bigger than 1. So this diverges by the ratio test. Recall that if we have a series from n equals 0 to infinity of a sub n, x minus c to the n, that'll, you plug 0 in and you get a sub 0. Plus a sub 1, x minus c to the 1, plus a sub 2, x minus c to the second, and so on, is a power series centered at c, where c is a constant. For a power series centered at c, precisely one of the following is true. The series converges only at c. The series converges for all of x. The series exists an r greater than 0, such that the series converges for that radius, and diverges if it's greater than r. R is called the radius of convergence of the power series. In part 1, the radius is 0, and in part 2, it is infinity. And I think to best explain this number 3 statement, we're just going to look at some examples. The corresponding domain is called the interval of convergence. All right, what are we talking about? Let's just do the ratio test for letter A, and in the end, we're going to look at the interval of convergence and the radius of convergence. So we have the limit as n approaches infinity of negative 1 to the n plus 2 times x minus 5 to the n plus 1 all over, let me get this a little higher, n plus 1 times 2 to the n plus 1. And then we will divide by this, but let's just do multiply by the reciprocal right away. So we have n times 2 to the n all over negative 1 to the n plus 1, and x minus 5 to the n. That's equal to the limit of, as n approaches infinity of, there's one more negative 1 on top than there is on the bottom, so that's going to put negative 1 at the top. So that takes care of the negative 1s. Let's take care of the x minus 5s. There's one more on top, so we have x minus 5. If we take care of those. If we take care of the 2 to the n and 2 to the n plus 1, there's an extra 2 in the denominator. So that takes care of that. And then we have n over n plus 1. Well, then we can split this up into the following. We have the limit as n approaches infinity. Let's just look at the n's here. We have the absolute value of n over n plus 1 times the limit as n approaches infinity of the absolute value of negative 1 times x minus 5 all over 2. Well, this part right here becomes 1. The limit of this rational function is 1, so now we're just interested in this limit right here. And if this series is going to converge, then negative 1 times x minus 5 over 2 must be less than 1. That is, the absolute value of this must be less than 1, so you can say that negative 1 is less than negative 1 times x minus 5 over 2 is less than 1. Now we just need to get x by itself. Well, let's multiply by negative 2. If we do that, we get 2 is greater than x minus 5 is greater than negative 2. And then add 5 to each of these, which leaves, let's add it this way. This will be 3 is less than x is less than 7. So the interval of convergence is from 3 to 7. And now we need to find the radius of convergence. And the radius of convergence is going to be half of this distance. Here's 3, here's 7. So if you take 7 plus 3, that's 10, divided by 2 is 5. 5 is right down the middle, so the radius of convergence is 2 units. Radius of convergence is 2. Let's do the same thing for letter B. Here we have the limit as n approaches infinity of the absolute value of x to the n plus 1 over 3 to the n plus 1 times, multiplied by the reciprocal, 3 to the n over x to the n, which is equal to the limit as n approaches infinity of the absolute value of, let's see, there's an extra x on top, and there's an extra 3 on the bottom. Well, this is going to converge as long as x over 3 is between negative 1 and 1. In other words, the absolute value of this has to be less than 1. So multiply everybody by 3, we get negative 3 is less than x is less than 3. So the interval of convergence is equal to negative 3 to 3, and the radius of convergence is just equal to 3. In letter C, we are going to do the same thing. We have the limit as n approaches infinity of the absolute value of negative 1 to the n plus 1, x to the, now remember we're plugging, this is the next n, so we have 2 times n plus 1 plus 1. So this is going to be 2n plus 2 plus 1. This is going to be 2n plus 3. So x to the 2n plus 3 all over 2n plus 3 factorial. It's the same thing. We would do the same process for the denominator as well. And then multiply by 2n plus 1 factorial over negative 1 to the n, x to the 2n plus 1. So we have the limit as n approaches infinity of, let's take the negative 1 first. There's an extra negative 1 on top. Takes care of those guys. On the top we have 2 extra x's. That makes x squared on top. And in the denominator, oh, we might have to write this one out. I have 2n plus 1 factorial over, this would be 2n plus 1 factorial times 2n plus 2 times 2n plus 3. So these cancel out, leaving 2n plus 2 and 2n plus 3. If we split this one up, we get the limit as n approaches infinity of the absolute value of, let's say, negative 1 over 2n plus 2, 2n plus 3. And I can leave the negative 1 with the n's instead of the x's because I know that this is going to end up being 0. As the denominator goes to infinity, this fraction is going to 0. Then we have times the limit as n approaches infinity of the absolute value of x squared. Well, this is 0 times x squared needs to be less than 1, but since we have a 0 here, that doesn't matter what x value we pick. So the interval of convergence is all reals, and the radius of convergence is infinity. So that part 3 where it talks about infinity, this is a case where we get that. You need to get a 0 in order to have this radius of convergence be infinity. Let's look at letter D. We have the limit as n approaches infinity of the absolute value of n plus 1 factorial x minus 3 to the n plus 1. And that's not a fraction, so we'll just do the division, of course. N factorial times x minus 3 to the n. The limit as n approaches infinity of the absolute value of, let's see, the top becomes n factorial times n plus 1. So the n factorials will cancel, leaving n plus 1 on top. And there's an extra x minus 3 in the numerator, so that leaves x minus 3. Well, that becomes the absolute value of, when we plug infinity plus 1, we get infinity, and then this is what we want to find a value for x for which this thing converges. So we just leave it as x minus 3. Well, if we're going to take the absolute value of this quantity, it will always be bigger than 1 except for one specific value. If we let x equals 3, then that becomes 0, and 0 times infinity is 0, and that is actually less than 1. So this series converges for one specific value, that is x equals 3, and that is the interval of convergence, and the radius of convergence is 0. There's no room. It's only one specific value that will allow this series to converge.